What would the vector from A to B be?
It would be -2 - 6.
Okay, which would be -8, right? And then if we flip those over, we wind up getting +13 and then +4. So actually, they turn out to be like just change the signs of everything, right? So the vector from B to A, this one, the vector from A to B is just negative, positive, positive. All right, so that's the mechanical part of this. Just make sure you get the order of those right, because if you do it backwards, it's wrong. All right, now special vector. There's a vector called the zero vector. And what makes it special is that it is a vector, but it doesn't really qualify when you think about the definition of a vector. Like the definition of a vector said a vector is an object that has a magnitude and a direction. What do you think the magnitude of the zero vector is? 0, so it has no length. But what about the direction? You see? It's a little bit of a problem when you talk about the zero vector. So it is a special vector. It's still a vector, but it doesn't quite have a direction. It has a 0 magnitude, but no direction. So this is the way we represent it. It's a 0 with that arrow, half arrow on top. And in two-dimensional space, the zero vector is that vector. And then in three-dimensional space, it's 3 pieces, right? Just remember that this is not the same as this, right? This is the number 0. This is the vector 0. These are not the same things. All right, components. So some more language here. If you're given a vector, right? Like let's say we have this vector, we call the vector in two-dimensional space v1 and v2, right? So those are like the numbers that are in there. These are called the components of the vector, not coordinates, components of the vector, right? The v1 is the x component, the v2 is the y component. If you're in three-dimensional space, then you'll have 3 pieces, 1, 2, 3, and those are the x, y, and z components, respectively. So we just have a special, language here, component, when we're talking about vectors as opposed to ordered triples and coordinates. Okay, we have with vectors something called the Parallelogram Law. It's a very nice law. This has to do with how we add and subtract vectors. So if you have 2 vectors, as you can see here, I have 2 vectors. One of them is called u, the other one's called v. If I attach the tip of one of them to the tail of the other one, try and do this here. So when I I take u, right? I take this is called the what of, this is the what of u, the tail or the tip? This is the tail of u, okay? There's the tip of u, and there's the tail of v and the tip of v. If I attach the tip of u to the tail of v, then the vector going from the tail of u to the tip of v is a visually, this is what the sum of those 2 vectors are, right? So this black vector right there is the vector u plus v. Now, why do they call this the parallelogram law? Because I could have done it the other way around. I could have, I could have moved this over like this. Okay, so notice I switched the way that I added them together. So now if I go v first and then attach it to u, then the net result is that I go from here to here, which is the same as the one that was down there. So I'm going to draw this one here so it doesn't move. That vector there. And let me put, I don't have blue, but there we go, like that. And I'll move that one back over. So do you see we have a parallelogram? So vector addition, when you add 2 vectors together, u plus v is the same as v plus u. Doesn't matter the order. So we have a commutative property of vector addition. and visually it draws parallelograms. So we're going to talk about a lot of properties of vectors, but we're going to try to do just a quick little exercise here. We're going to do v plus u first. So I gave you the vectors, and we're going to try and add them together. So I'm going to take v, and I'm going to add u. All right? So what I'm going to do is I'm going to leave v alone. Okay? Take u, and remember I can move u around. I just can't change its length, can't change its direction. So if I want to draw the vector v plus u, then I'll take u, I'll slide it over here, and I'll slide it down like this. So over, down. It'll look something like that. That's u. So v plus u would be the vector going from here to here. That's v plus the vector u. Right? So starting out at the tail of v, where do you end up? Right here. So tail, tip. How about u plus w? Okay, so I'm going to take the tip of u and put it to the tail of w.
Yes.
So I can either move this one down and over, or I can move this one up and over. It doesn't matter which way you do it. Okay, so just for ease of visualization on your end, I'm going to just take this one and move it up and over. Roughly, that's it, right, w. So u plus v will start here at the tail of u and end up at the tip of w. So that's u plus w. How about v plus u plus w? Three of them together. Couldn't I just do, this one right here is already u plus w, isn't it? From here to here. So couldn't I just add v to that? And v is right here, right? Mm-hmm. So if I take that v and I move it up and over and attach it to that, then I would get the result. But I think that it's going to be too scrambled up, so I'm just going to start over. So let me do this. I'm going to go this one to this. So there's u. And then I'm going to go v up and over like this. And so the result would be that vector right there. Okay, starting here, go through all three. So the net result is going from here to here. Whoa. All right, so that's just some visualization. What about subtraction? What about subtraction? How does subtraction work? Addition, we're just going tail to tip, right? Tip to tail. This looks like we're just moving them around. So how do you think subtraction works? Yeah, okay, so we haven't talked about negatives yet. So, you know what I'm saying? Like, that's what's going to happen. But let's say we do a vector u, and then let me do another vector v, like this. If we want to subtract these, then we do u, take away v. How do you think that's going to work? Yes, go ahead.
Putting the tail to tail?
Tail to tail. Will that work? Let's see. Let's just see what happens, all right? Let's see what happens. So let's do this first. Before we do that, let's do our standard. If we added them, then we would just go up and over. So this would be, that would be my v. And then this vector right here would be u plus v, right? That's if we added them. That's not what we're looking for. So the suggestion here is we put them tail to tail.
Yes.
And see what happens. So if I take this one and I move this one here, like this, tail to tail, then what vector are we talking about then? Because you know these I've been going up and through it like that and then just connecting. So what vector are we? Maybe
Tip of u to the tip of v.
tip of u to the tip of v. So maybe it's this one. Whoa, wow. Okay, that's supposed to be straight. Maybe it's this one. Maybe that's what that is. Or perhaps it's the other way. Maybe it's from here to there. Maybe. Maybe. So we don't have a clear reasoning for this yet, right? So we need to introduce something, kind of understand something before we can do this. And that is the idea of scalar multiplication of a vector. So I'm going to get to that next. I just wanted to show you that it's not as direct. This might work. Tail to tail might work, but there's nothing yet that's convincing that it will. So here we go. Scalar multiplication. If we have a vector v is given to us, and then someone gives us a scalar, which is just like a number, then how does multiplying by a number change the shape of v? Well, the first thing is that if the absolute value of the number is bigger than 1, it's going to stretch the vector, make it longer. If the absolute value of the number c is between 0 and 1, it's going to shrink it. And if the number itself is negative, it's going to flip the vector over. So here's an example. So here's my scalar. If I take some vector, so these are supposed to be angle brackets, but my computer doesn't do that easily. So this is the vector 3, 3. If I multiply it by 3, I'm going to get the vector 9, 9. So it takes the vector v and it stretches it out, right? Because I multiplied it by a number that's bigger than 1. If I take that number and I scale it by 0.75, then it's made a vector in red here that's shorter than the original one. And if I make the number in front negative, it's going to flip it to the other side. So that's, if this is v, negative v is going to point at the opposite direction but have the same length, right? So does that help us see how we can handle this u minus v? How do you think we can handle that? Can we look at this as u plus negative v, right? And what is negative v compared to v? It just flips it in the other direction. So let's go back and take a look at that example I just had, and let's figure out, does it wind up being tail to tail? So I gave you, it was, I think u looked something like this, right? And v was something like, maybe it wasn't that long. There was v. Maybe it wasn't that long. Right? We had something like that. And I asked to do u minus v. So what I'd like for us to do first is figure out what's negative v. So negative v would be this vector, opposite direction. There's negative v, right? And now let's add that to u. So I'm going to just take this, slide it, move it up, and attach it to the tip of this. So that would put me like this. That's negative v. So what would the net result be if I did u followed by negative v? U followed by negative v would be the vector going there to there. Okay? Now, the question, or I guess the thing we were kind of hung up on was it really tail to tail? Was it tail to tail? So I have to draw this again. I'm sorry, I'm kind of scrambling all over the place. But here was u. We took v down here. We did tail to tail as a suggestion from, what's your name again?
Matthew.
I haven't asked you, so Matthew. Yes? Matthew suggested tail to tail, but then the question was it the vector from here to here or the vector from here to here? Right? And I didn't quite draw it right. But so which vector does it turn out being? V to u. It's this one. That's the vector u minus v. Pardon?
And that works out.
And it does. Yeah, it does. It works out that will be This vector right here is the same as this blue vector here. We would have to do it all on one sheet of paper to convince ourselves, like do actual numbers. But it turns out that if you want to know what u minus v is, what you can do is you can put u and v tail to tail, and then draw the vector that goes from the tip of v to the tip of u. All right? I can tell a lot of you have seen vector stuff already. All right, so what about the idea of vectors being parallel? This is kind of a weird thing. Because when we think parallel, when we're talking about like parallel lines, we're always talking about lines that have the same exact slopes, right? Vectors, the definition of parallel vectors is slightly different. It says any two vectors are said to be parallel if they are scalar multiples of one another. That's the definition. So look at this vector right here. If I draw this vector, right, call that u, then I draw another vector, let's say like this, call that v, are they parallel? Are those vectors parallel? Yes. They are parallel. Now, why are they parallel? Can you take u and multiply it by a number that would give you v? Yes. I would have to, first it would have to be negative, right? So I'd have to take some number, multiply a negative number in front of u, and then I have to shrink it to make it smaller. So these two vectors are parallel. Now I don't know what the number is. See, what I'm telling you is this. V is some scalar multiple of u. And all I know right now, just but visually, is that c has to be negative for this to work. Now, you could also have a situation like this. What if I give you a vector u like this, and then I give you another vector like this that's the vector v? Are those parallel? Yes. V is a scalar multiple of u, but this time the c would have to be positive, so it points it in the same direction. The only time you're not parallel is if you don't have the same direction, right? If you don't have the same direction, right? I shouldn't say that. Yeah, there's not an easy way to say that, is there? The only way to be parallel is if you're a scalar multiple. I mean, that's the easiest way to say it. You're either pointed in the same direction or you're pointed in the opposite direction. Okay. What's that? That's the definition of parallel. I guess the idea is this. Parallel can have different meanings depending on what you're talking about, right? I'll give you an example. True or false? True or false question. Two parallel lines never intersect. True or false? True or false? So let's do, I like doing voting this way. Everyone has to close their eyes and raise their hand. That way you don't see what other people are doing. So you ready? Real quick, close your eyes. True or false here? Two parallel lines never intersect. Close your eyes. True, raise your hand. Okay. False, raise your hand. Okay. All right, that's good. So trues were overwhelming. There were a couple of falses. So let's question these falses here. Who said false? Do you want to? You said false, you said false. Any sort of, you want to make an argument for it? On a sphere? Like, for example, like longitude lines? So you're on a sphere then? Where was everyone else? On a flat sheet of paper. That's correct. So this question is false because it depends on where you are. All right? So if we're talking about Euclidean geometry, flat sheet of paper, two parallel lines never intersect, that's true. Okay? But if you don't specify the geometry, then you can have two parallel lines intersect, like longitudinal lines. I'll give you another example. So that's spherical geometry. It's not Euclidean geometry. Euclidean is like, x, y, x, y, z, like we drew the right-hand rule. That's all Euclidean geometry. Another example of a non-Euclidean geometry where this would be false would be, here's Euclidean. I'm going to draw you a street. I'm going to draw you a couple of buildings next to the street. This is a top view. Pretty good? You like it? Pretty impressive? Okay. Now I'm going to draw you that same street in non-Euclidean geometry, using some non-Euclidean geometry. So okay, I won't draw the buildings on the other side. Okay, now Euclidean geometry, parallel lines. These are all parallel lines. They never intersect, right? Okay, this is called perspective geometry, and all parallel lines in perspective geometry intersect at a vanishing point. Right? So this is how you trick your eyeballs into thinking you're seeing 3D on a flat sheet of paper. So parallel lines do intersect here. They don't here. So it all depends on the geometry. The question was, why do they call it parallel, right? That's what this all came from. Parallel has different meanings in different places, right? And it behaves different in different places. So in vectors, when we're talking about vectors, parallel just means scalar multiple of one another. That's it. Throw away your Euclidean idea of parallel now. Does that kind of help? Okay. All right. So two vectors are parallel if and only if they are scalar multiples. All right, how about the length of a vector or magnitude of a vector? How do we find its length? Well, all we do is we take the vector and we take the square root of the sum of the squares of the components. So that looks very much like Pythagorean in two-dimensional space and in three-dimensional space. And the notation we use is the same as the absolute value symbol from numbers. And that's what we use to represent the length, or it's also called the norm of the vector. All right, so that's just a formula. All right, we have a lot of examples here. Let's do example 4. Let's do part D. All right, so what we need to do is we need to find the magnitude of taking 4 times v and subtracting 3 times u. So this is all this is just mechanically can we do vector operations. That's all this is. So let's figure out first what 4v is. So what's 4 times v? This is scalar multiplication, right? I'm going to multiply 4 times the v vector, which is the same as multiplying 4 times the vector v is 2, 3, negative 5. So all you do with scalar multiplication is just pass the 4 through. It's like distribution. So this should be pretty clean here. What do we got? 8, 12, negative 20, right? That's 4v. We also need to do 3 times u. So 3 times the vector u, which is negative 5, 7, negative 2, which is negative 15, 21, negative 6. Now I should subtract those, right? So I need to take this one and subtract this one. And then at the end of that, I'll do my magnitude. So 4v minus 3u should be the vector 8, 12, negative 20. Subtract from that negative 15, 21, negative 6. So when we do this algebraically, all we do is component by component. So 8, you're going to take away negative 15. 12, you're going to take away 21. And negative 20, you're going to take away negative 6. So be careful with that. So y'all help me out here. What do we got? So we're going to do 8, and we're going to take away negative 15. 23. And then we're going to do 12, and we're going to take away 21. Negative 9. And then we're going to do negative 20, and then we're going to take away negative 6, which is the same as adding 6, so negative 14. So that is the vector 4v minus 3u. And now we need the magnitude of that. So to do the magnitude of 4v minus 3u, we're going to do the square root of the squares of each of these added together. So we do 23, someone's going to need a calculator for this, plus negative 9 squared plus negative 14 squared. It's going to be a pretty big number in there. Inside or after the root? What is it? 806. Okay. That's it. Yeah, we'll leave it. You can do a decimal here, but we'll just leave it. What was your name?
Danny.
Danny? Okay, thank you, Danny. We're going to trust Danny's answer, yes? Okay. That's just arithmetic, right? So this is just, we're just trying to get mechanics out of the way here. All right, unit vectors. So what is a unit vector? That's a special name. A unit vector is a vector of length 1. Okay, so any vector that has a length of 1 unit long, is a unit vector. The question is, if somebody gives you a vector, any vector, can you come up with a vector that has the same length, has the length of 1? So if someone gives you any vector that's non-zero, a blue vector, can you find me the red vector, which is pointed in the same direction, but has a length of 1?
Yes.
It seems like you could, right? You're going to have to do something to the blue one. So if someone gives you this blue one, if you want to find the red one, which has a length of 1, you're going to have to somehow scale the blue one, right? Shrink it or stretch it, depending on the blue one. So what should let's see if you can't figure this out. Let's say I give a vector and it's 4 units long. How can you make that have a length of 1? Divide what? Divide it by 4, right? And that would give you a length of 1. So we would want to divide each component by 4 to shrink it. What if the length was 3? Divided by 3, right? So if someone gives you a vector, in order to figure out what a vector is that's pointed in the same direction with the same length, with the length of 1, we have to divide it by its own length. And that's what the formula here is saying. Somebody gives you a vector, given any vector u, in either 2 or 3 dimensional space, we can always find a unit vector in the same direction by taking the vector u and dividing it by its own length. Look, everyone, that's a vector, isn't it? The magnitude of u is a number. So if you rewrite this, 1 over the magnitude of u, that's a number, right? That's a scalar multiple times u. So that's the thing that shrinks the u down to make it a length of 1. So this, again, is just something that's computational. Let's find the unit vector that points in the same direction as that vector v. So what would be my first step? I want to find a unit vector in the same direction as that one. Just find the length of that first. Okay? So the magnitude of that would be the square root of each of those squared, add them up. So 4 plus 9 plus 25, which is root, what is that, 38? Root 38. So now what I want to do to find this unit vector is I want to take 1 over the magnitude of v and multiply it times v, which means 1 over root 38 times the vector 2, 3, negative 5. So there's my 1 over magnitude of v times the vector v itself. And how do you multiply that through? Just right through, right? Each component gets multiplied by that. So it's 2 over root 38, 3 over root 38, negative 5 over root 38. So this vector should point in the same direction as that one, have a length of 1. And you can check it by just taking the magnitude of it. If you take the magnitude of this, you'll see it's 1. But I won't do that. All right. Standard basis vectors. So there's some important vectors that we use in a lot of application courses, physics, chemistry, engineering, these standard basis vectors. Now you may have heard of them, I hat, j hat, k hat. Have you all heard those before? So I hat, j hat, and k hat. Let's first talk in two-dimensional space. Okay, two-dimensional space, you have this thing called I hat, which is the vector 1, 0. And then you have the vector j hat, which is 0, 1. And the reason these are called standard basis vectors is that every single vector out there in two-dimensional space, every vector that you can ever come up with, is always just this vector scaled plus this vector scaled. So if I want to create this vector u, then what I could do is I could take the vector, this is I hat, I know it's hard to see that, but this is I hat, that's j hat. If I multiply I hat by a number, in this case 2.11, I'll be here. If I take j hat, multiply it by a number here, in this case 2.66, I'll be here. And then if I attach these tail to tip or tip to tail, I'll wind up here by the parallelogram law. And that works for every single vector you can ever come up with. There's always some way to get to that vector using those two. Anyone taken linear algebra? Okay, so this is basically we're saying that these two vectors span the space R2. So they're basis vectors. But they're actually more important, they're even more important because not only do these two vectors form a basis for R2, they're what we call an orthonormal basis, which means that these two vectors are actually orthogonal to one another, and they each have a unit length. So like these are like the super best basis vectors that we can get in Euclidean geometry is the I hat and j hat. They span the whole space, they're orthogonal to one another, and they all have a length of 1. Orthonormal basis. Now in three-dimensional space we have the exact same thing, right? Except now each of the I hat, j hat, and k hat have to have 3 components. So I hat's 1, 0, 0, j hat 0, 1, 0, and k hat is 0, 0, 1. And again, you can span the whole space. I don't think I have a visual for this, but you can span all of three-dimensional space with those 3 vectors. So some of the notation that you're going to see that I use here, I do not like using I hat, j hat, k hat notation. I think that's just mathematician in me versus the physics part of me. So when we see a vector like 3 I hat minus 2 j hat plus 4 k hat, please understand that I'm not going to ever write this way. Okay, the way I'm going to write this is I would look at that as being I hat, j hat, k hat. Okay, so there's your ijk. And then I'm going to scale through, so I'm multiplying my 3 through here, my negative 2 here, and my 4 here. And so I'm going to get the vector 3, 0, 0, minus the vector 0, 2, 0. Then distribute here plus the vector 0, 0, 4. And so I am going to write it, when I add these all together or put these together, I'm going to get the vector 3, negative 2, 4. So you will never see me write 3i hat minus 2j hat plus 4k hat. You'll always just see me write 3, negative 2, 4. These are the same thing, all right? Just different notation for the same exact thing. I just don't want you to feel like you're doing something completely different because I'm not using I hat, j hat, k hat. There's also, I've seen, when I was a student, I had vertical vectors written this way. It's another notation for vectors. So you'll see that in different fields, different applications, we write our vectors in with different notations. I hat, j hat, k hat, angle brackets horizontally, vertical columns. It all just depends on where you are. How we doing? Still got almost another hour. Jeez. Brutal. Brutal. All right, I'm done with this section. We are still just reviewing stuff that a lot of you have seen, so just keep that in mind. This will become something hopefully new to you soon. How many of you have seen the dot product? Obviously, so many of you saw the vectors. I'm sure you've seen dot product. So then you tell me, since you've seen it, what is the dot product of two vectors? Does it have a geometrical representation? Does it have any sort of meaning? I know you know how to do a dot product if you've learned it, but what does it mean? If I tell you, here's a vector, and here's a vector, and I ask you to find the dot product of the two vectors, what have you just found?
The angle.
It has something to do with the angle between them. Yes, it does. Something to do with it.
So I thought when you multiplied everything out and then canceled, what's that do?
Canceled stuff.
No, I think it's enough.
Okay, so what the hell is the dot product? Let's see. I mean, I think if you've seen it, that means you mechanically have done it, but what does it mean? And then we actually have, how do I say this? If somebody gives, let's kind of back up, okay? Take a step out for a second. If somebody gives me a vector, and I say multiply it by a number, what is that going to do to the vector? It's going to scale. It's either going to stretch it, shrink it, or flip it over in the opposite direction, right? That's called scalar multiplication. Give me a vector and a number, a scalar. I have an idea of what that operation is, right? Scalar multiplication of vector. So we have one type of multiplication when it comes to vector, scalar multiplication. There are two more types of multiplication when it comes to vectors. If I take a vector and another vector, I can put those together with a dot product, which I'm about to talk about. And then there's a third operation called the cross product. Take a vector and a vector, cross them, and I get something. All right? So we have three types of multiplication when it comes to vectors. When you're learning about numbers, right, back in elementary school, they gave you like, okay, we're going to do 4 times 7, right? They didn't tell you that there's 3 different types of multiplication to do 4 times 7, right? It was like 4 times 7 is 28. That's it. There wasn't like, do you know what I'm saying? There's only one, multiplication only meant one thing. Here with vectors, we have 3 types, scalar, dot, cross. All right, so dot product. What is it? What does it mean? How do we do it? What the hell meaning does it have, right? Why is it important? I don't know why this is so big. All right, so given two vectors, v and u, where v has got 2 components, v1 and v2, and u has got 2 components, look at what the computation is to get the dot product. You do u, and then you put this like kind of bold dot, u dot v. All it is that v1 times u1 plus the v2 times u2. So it's just multiplying the components together and adding them. So like actual mechanics, dot product is super straightforward, right? Sum of the products of components. The important thing is that your answer is a number. Now this is weird, and this should bother you a little bit, because this is one of those first times in math that this ever happens. Like if I tell you do 4 times 7, you get 28, right? Number times a number, you get a number. Sir? You gotta go. You gotta go. Come back next time, awake. It's okay, but it's not an option at this point. You have to leave.
You back next class?
Yep.
So sorry.
Don't let it happen again. All right. So if you take 4 times 7, 2 numbers, put them together, you get a number, right? Even with the scalar multiplication, take a vector and a number, we put them together, and we got this vector out. Here, we're taking 2 vectors, we're doing an operation, and we're getting a number. It's like cat plus cat equals dog. You know what I'm saying? Like, it's weird. What does the number mean? Well, let's look at it. Let's look at the visually what it is, all right? This is just saying if we have a vector in 3-dimensional space, that when we dot them, it's the same thing. Components, 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 add them together. We'll do it. But I want you to see it visually. Where is it? Hold on. No. Yeah. So I have 2 vectors here. Okay, there are my 2 vectors. I have the computer calculating my dot product for me. All right? So right now, can you all see that says 7.7 there? So the dot product there is 7.7. Let's see what happens if I make this one shorter. What's happening to it? It's getting smaller. Okay, if I make it longer, dot product's getting bigger. What if I move these vectors closer to one another? It seems like it's getting larger. Well, it seems unpredictable, doesn't it? Like shorter, longer, it seems like it might be hard to figure out what's going on here. Let's kind of turn it and let's see, what's happening? Oh, and then now what? Negative, right? Negative. Negative, positive, negative, positive. So what about right in between there? What is that? 0, right? Between positive and negative numbers, 0. So it looks like when I get to about what, it goes to 0. 90 degrees. And actually, this is going to turn out to be the most powerful property we have for dot product, is that it's going to be a way of checking for orthogonality, for perpendicular, for 90-degree angles. But we're not there yet. I just want you to see that this seems to be leading us in that direction. If the angle between our 2 vectors is less than 90 degrees, it looks like we're getting a positive answer for the dot product. But if we let the angle between the 2 vectors be bigger than 90 degrees, then it looks like we're getting a negative answer. What happens if we go 180 degrees? It's still negative, right? And then we go all the way around, come back, positive again. See that? So something interesting is happening here. We'll have to kind of lead our way up to that. Now, I'm sure you can all do this dot product, but let's just do it, all right? What is u dot v here? Okay, so you're going to just multiply the components together. 2 times -3, -6. Add to that, -3 times 4. And then add to that 5 times 7, so 35. So we get a numerical value here. What do we have? 17? 17. Is 19? 17, right? A number. two vectors, all complicated three-dimensional vectors, and we get this number 17 out. Still don't know what it means. We think this means that the angle between them is less than 90 degrees though, right? Okay, so we still don't know what this is. All right, let's talk about some properties of the dot product before we actually get into the meaning of it. Check out this property, super important property right here, the first one. If you take a vector and dot it with itself, you get the magnitude of u squared. So let's prove that. If I take the vector u1, u2, and I dot it with itself, u1, u2, then by definition, I'm going to do u1 times u1, which is u1 squared, plus u2 times u2, which is u2 squared. Right? All right, that's what u dot u is. But then what's the magnitude? What would be the magnitude of u? We looked at that earlier. That's the square root of u1 squared plus u2 squared, right? So these aren't the same, right? But if I square this, they're the same. So that's where this property comes from. The dot product of a vector with itself is equal to the length of the vector squared. What does the next property 2 say?
Order doesn't matter.
Order doesn't matter. U dot v is v dot u. And that comes directly from the idea that multiplication is commutative. You can flip it over. Okay, look at this one here. If you take a vector u and dot it with the sum of two vectors, it's almost like the dot product distributes over addition. So it's like you go u dot with v, and then you go u dot with w. What about this fourth property? Scale the vector u, dot it with v. Saying here that you can do the dot product and then scale after. Or if you want, you can put the scalar on the v and not on the u. So basically that c, that scalar, slides around the dot product anywhere you want it. And then the last one here says that if you take the 0 vector and dot it with any vector, you get 0, the number 0. Does that make sense that that would work? Because 0 vector has just 0, 0, 0 in it, so when you multiply it out, you get 0. All right. So those are some properties. And that's the one I'm not ready. Well, yeah, I'll give it to you, but then we're going to prove it. This is kind of like the main result of this section. This is a major formula, the dot product theorem. It says if the angle theta between two vectors, if theta is the angle between two vectors u and v, then the following is true. That the dot product is the magnitude of u times the magnitude of v times cosine of the angle between the two vectors. So this is what was, you were saying something about the angle between them, right? So yes, the dot product has some connection between the angle between the two vectors, but also is connected to their lengths. So I'm going to go back to that visual. I'm going to prove that formula to you in just a second. I'm going to go back to that picture. So if these two vectors are sitting here, if I make one of them longer, right, its magnitude is bigger, then it should make my dot product get bigger. So that's why when I went out with this, see how it got bigger? When I make it short, it's going to make it smaller. Same thing with this one. Longer makes it bigger, short, smaller. Now, why is it getting smaller when I close the angle off? What does cosine do as your angle gets small? Maybe we should look at cosine. This is your cosine, right? Goes to 2 pi here. Here's pi, right? So we are only interested in that part. Why would we stop at pi? The angle between two vectors, right? If I give you two vectors, the angle between them, the smallest it could be is 0, and the biggest it could be would be pi, right? If I go around, then the angle between them is this angle, and that's still smaller than pi. So we're going just between 0 and pi. So if I make this angle between them small, right, really small, right, then what is cosine going to do when they're real small? What is it headed towards? 1, right? Cosine of 0 is 1. So what would happen if the angle between them is 0? What's the dot product then? What is it? Well, cosine is, that cosine part's 1, but what about that part's in front? Is magnitude of u, magnitude of v, right? So wouldn't the dot product just be the length of one of the vectors times the length of the other vector? That's exactly what it would be. That's not very useful, but that's what it is. Okay? But the big thing is this part. When this becomes 90 degrees, what's cosine of 90 degrees? 0. See, that's here. And so I know that if the angle between two vectors is 90 pi over 2, that that the dot product will have to be 0. And then it can be shown in a theorem that if your dot product is 0, then they must be orthogonal to one another. And that's going to be a major result. But I think it's worth us talking about why this is true. Because all I've done is I've told you, hey, this is true, right? I said, hey, there's the big formula. There it is. Would you all like to see why that's true? I think it's worth seeing. Okay, so here's how we're going to do it. Remember, what I'm trying to prove to you, I'm going to put it over here on the side here. I want to prove to you that u dot v is the magnitude of u times the magnitude of v times cosine of the angle between the two. Right? That's what I'm trying to prove. All right, so here's the way I'm going to prove it. First thing I'm going to do is I'm going to draw a picture. So I'm going to do this in three-dimensional space. There's the origin. Here's x, here's y, here's z. All right, so here comes, I'm going to draw a vector for you. Now remember, vectors can move around, right? So I'm going to draw a three-dimensional vector out here, and I'm going to move it to where it's positioned at the origin. Okay, I'm going to call that vector u. Now it's not flat up against the yz plane. It's just sitting out there, okay? Then I'm going to draw another vector. Don't have really good markers in here. Another vector here. That's my vector v. Next thing I'm going to do is take a look at this triangle here. Okay, and just to make things easy, let's call this point A, that's the origin, point B here, and point C here. Okay, so those are these points. And let's call the angle between them that angle. So I've got a vector u that I move to the origin. I've got a vector v that I move to the origin. And then I've created a triangle out of these. And I'm looking at the angle between those. I'm calling that theta. All right? So there it is. Now I'm going to go back to pre-cal. And I'm going to go back to the law of cosines. So let's see if you remember the law of cosines. Law of cosines. So if somebody gives you a triangle like this, and let's say this is side A, angle A, side B, angle B, side C, angle C. Law of cosines would say, there's three of them, aren't there? There's three different versions of the law of cosines. So give me any one of those. A squared equals B squared plus C squared minus 2BC cosine of A. That's one of them.
Yeah.
And then there's two more. B squared equals A squared plus C squared minus 2AB cosine B. Anyway, can we just know that that's there and we can take that on faith? Yeah. Okay. So now let's go back to this and let's look at what we have here. we have, this theta is like the angle A over there. You'll see that? It's like, you'll see that? I can say that's A. Then, okay, what's A squared? A squared is this side squared, yes?
Yeah.
For us, that's this distance here. You all with me? Okay, what is the vector that goes from here to here? The vector that goes from here to here? U minus V. Minus V. Remember we just did this tail to tail?
Yeah.
Okay, so the vector that goes from here to here is U minus V. Agreed? So I'm trying to fill out this formula here. This side right here is this side right here. So this is U, the vector U minus V, its magnitude. That's this to this, yes? Okay, equals, according to this, what would come next?
U squared.
B squared, which is this side or this side, doesn't matter which one I use. So this side, its length squared. What's the length of this? Length of V squared, right? Plus the length of U squared, that's this side, minus 2 times the length of vector V times the length of vector U cosine of theta. Okay, I hope you can follow that. That's just me translating everything over, yes? Oh, you know what? I forgot to square that, didn't I? Did y'all see that?
Yeah.
The length of A squared, I forgot to square this. My apologies. Are we good? You sure? I'm trying to prove this right here. All right, I don't need this anymore. This is a very, very relaxed proof of this, all right? So I realize I'm going kind of through this a little sloppily. Take a look at what I just did on that left side and tell me what I'm doing. Or like, tell me what I did on that left side.
You're going to distribute.
Yeah, but how did I get to that? Why did I write that down? Like, what is...
This square is square.
Is this right? So do you remember I said the very first property? U dot U was equal to what? Very first property. Magnitude of U squared. So if I have some vector squared, the length of a vector squared, it's equal to the dot product of the vector with itself. So if I have some vector, its magnitude squared, that's equal to the dot product of the vector with itself. Yeah. And now what we can do is use the distribution of the dot product to basically turn this into U squared, right? And then what? Minus 2U dot V, right? And then what's the last thing here? Plus V squared. Hold on. Missing my magnitude. Hold on. Did I lose my... Oh, yeah, never mind. Just ignore me. Yeah. Let me rewrite this. Hold on. We have to be careful with this notation. When we're doing this to this, this is U dot U. Okay? U dot U. And then minus 2U dot V's. And then plus V is V dot V. Okay. Okay, there we go. And then that equals magnitude of V squared plus magnitude of U squared minus 2 magnitude of V magnitude of U